So let's continue taking an informal look at what we mean by limits. So in the previous film, we discussed the fact that lim fx, x goes to a is equal to L. What that basically means intuitively is that if you have some type of graph, here is A, then the limit here is basically where you end up when you let your finger trace the graph as the x value tends to A. So whatever height this here is, that should be the value of the limit. And of course, we're going to define what this means abstractly, but intuitively, this is usually good enough. Now, there are some cases here that can be confusing. And the rule of thumb, let your finger trace the graph, is actually good enough to kind of safely guide you through this. So let me take exactly the same graph, but let's say that over the point A, we're not taking this value, but instead we're taking this value. Let's call this 1, and let's call this height, well, a half then. What is the limit now? Is it a half or is it 1? So notice when I do this, what I'm meaning here is that f of a is equal to 1. But what I said earlier about intuition still holds. So if I now let my finger trace the graph as the x value goes to a, then at what height do I end up? Well, I end up here. I tend towards this height. So the limit actually doesn't care what happens at the point, only cares what happens as we approach the point. So the limit here is still the same height, which, well, I gave it the name a half here, which is not equal to 1, which was f of a. So it's not the case that lim x goes to a f of x is always equal to f of a if the function is defined there. And keep in mind, we really want to use the limit as a tool to figure out how functions act close to points that they're not defined. This also means that if I delete this, so let's just say that here a is not inside of the domain of f, nothing changes. When my finger follows the graph as x goes to a, I'm still tending towards this height. So in fact, the limit really doesn't care what happens at that point. It doesn't care if it's in the domain, and if it's in the domain, it does not care what the value is there. And this is something we'll see when we write up the formal definition of the limit, that in the formal definition of the limit, the value of f at the point is not at all used. So the definition of the limit is completely independent of what the function actually does at that point. The thing is to capture what it does as we approach that point. So one more thing I want to bring in is the fact that we can have graphs that look, for instance, like this. So let's say we attain this value, but then we make a slight movement in the graph. So let's say that, well, here we have the value a half, and here we have the value a quarter. Okay, we still call this point A. What can we now say about lim x goes to a f x? Well, the thing is, this finger rule of thumb, this finger intuition is still true. It still guides us. So when I come from this side, I want to approach a quarter. If I come from this side, I want to approach a half. So this gives me a different value depending on which side I come from. So what does my finger say? Well, my finger is confused. And when my finger is confused, that's really bad. So this means here, this limit does not exist. So you can say that whenever your finger is confused, it means that the limit does not exist. But all is not lost, because even though the limit doesn't exist because we're getting a different value from the sides that we approach a, we still have what we call one-sided limits. Okay, so here we can say, but if I approach from the left, I reach a half, and if I approach from the right, I reach a quarter. So this is useful information. So that's why we define the one-sided limits. So approaching from the left, I put a minus here. So we approach a from, you could say, its negative side. And in this case, we write a half, and then lim x goes to a from its positive side, f of x is equal to a quarter. Okay, but of course, these two guys are not equal to each other in this case. There's actually a theorem which we can prove, is that lim x goes towards a f of x is equal to some value L. So the limit exists, such as it does here, if and only if the limit from the right and the left are both in agreement. So this means two things. This means that if I know that the limit exists such as this, then I immediately know that the left and the right limits both exist and are equal to the same value. And conversely, this means that if I check my one-sided limits first, I notice that they agree, then I can immediately conclude that the usual limit exists and is equal to that common value. So for this reason, we call this the two-sided limit sometimes, and these guys the one-sided limits. But keep in mind, if I talk about the limit without specifying if it's one or two-sided, I usually always mean that it's two-sided, unless, of course, I'm looking at a function near the endpoints of its domain. In that case, the limit is automatically considered to be one-sided, if it's not possible for me to check the limit from two sides.